Okay, so this next section is the pathways of blood, and I already went over this in the very first slide of this set, but I just want to let's go over it again. So a very simple path means we're going to go from arteries to arterioles, okay, to capillaries, then to venules, and then to veins. Okay, so here's a simple pathway. Okay, so that lines up there. Okay, now, of course, it's our body. Nothing is ever simple, right? So there are alternative pathways. So the alternative pathways lots of times involve anastomosis, which I think we talked about in the last lecture. So an anastomosis is where two vessels come together, or two or more vessels come together. So it's kind of like here's one, here's another one, maybe here's another one. This would be the anastomosis. So that's like where they meet and they branch apart. So the cool thing about anastomosis is they're going to allow more than one way to flow. So it's like our body's backup plan. Okay, so the first alternative pathway is an arterial anastomosis. So you can see them right in here. So there's just a whole bunch of different flow ways or pathways that the blood flows through arteries. So we have those in our abdominal wall. Okay, no big deal. Okay, now, venous anastomosis, those provide different drainage paths. And there's actually a lot of these in our body. So here's an example of venous anastomosis. We have them, one place where you'll learn is in your upper arm or in your upper limb. We have 3 vessels that are going to drain the upper part of that extremity. You'll learn those when you get to blood vessels. But there's just a whole bunch of different pathways for the blood to drain. So if one is closed off, like if you're laying on it, there's a different way for the blood to get back. Okay, now the third one is an arteriovenosis, which is a shunt. Okay, so here's that. What happens with it is we totally bypass something. So we're going to shunt around it. Okay, so it's almost like a little shuttle. You go around the capillary bed, and we don't need to take the blood to the capillary bed. So an example of that is if you're cold or you're hypothermic, what happens is your body is trying to keep the core warm. So the arteries will shunt the blood straight to the veins, and it won't take it to the capillaries in your fingers or your toes or your ears. Okay, now the fourth one is a portal system. What a portal system is it's 2 capillary beds that are connected by a vein. So it's a capillary bed, and then a vein, and then another capillary bed. The best example that we have of that is the hepatic portal system, which you will learn. Okay, so the hepatic portal system is how blood gets from your digestive organs to your liver. But for right now, all I want you to know is it's a series of 2 capillary beds. So it's like we go through one capillary bed, and then we go through another capillary bed. Okay. All right, now this slide, what I want you to get from this, the whole take-home message, is I want you to understand that the blood, when it goes through the capillaries, the flow really, really slows down. So if we look at this red line, okay, so here's arteries, arterioles, capillaries. Okay, by the time we get to the capillaries, the velocity of the blood is really, really slow. And it stays slow through the venules and the veins. And then when it gets close to the heart again, it picks back up. Okay, so I always say think of water in a river. Okay, so the water's going in the river, and it's flowing pretty fast. And then it gets to where there's a dam. Okay, it slows down when it gets to the lake. It's not moving. Okay, so that's what's happening at our capillaries. That's going to be really, really important so that we can have gas exchange and nutrients exchanged and waste picked up. So we need it to slow down so we have more time. If it's going through there really fast, we can't pick it up. Okay, now, how are things exchanged at the capillary beds? So how does the magic occur? So the first one is diffusion. So diffusion is, you guys know, it's just the movement of things from a high concentration to a low concentration. And things that are going to move through there are small particles, so ions, and then things that are lipid soluble. So oxygen, carbon dioxide, ions, things that can dissolve in lipids. Okay, so they can go through intercellular clefts, okay, which will be spaces in between the cells. Okay, and they can go through fenestrations, which are holes in the cell. Okay, now, no proteins diffuse through. Proteins can't diffuse through. They're too big. Okay, and then it's also important to remember that these cells over here are cells, okay, so they could have facilitated diffusion and active transport occurring too. Okay, the next kind of movement is vesicular transport, which is like endocytosis, exocytosis. So at the apical surface, we'll have pinocytosis, where things are being taken in. Okay, they're taken in, and then they'll be exocytosed out. Okay, so this bulk transport or vesicular transport is going to be really important for big molecules that can't diffuse. So proteins, one protein is albumin, some big hormones. And this little picture kind of shows you how things are moving through pathways. So fenestration are holes, then we can have diffusion between cells, vesicular transport. Okay, now, how are things exchanged at the capillaries? Continued, okay? So another thing, important concept to get talking about capillary exchange is bulk flow. Okay, so bulk flow is the movement of large amounts of fluid and the things dissolved in the fluid in one direction down a concentration gradient. Okay, so it's the blood and the things dissolved in the blood. Okay, now we have two different terms, and you really, really need to know what these terms mean, because people get them confused all the time. Okay, so the first one is filtration. So filtration occurs, everything got moved around when I imported it. Filtration occurs at the artery end. Okay, so this is the artery end of my capillary that I drew. Okay, and then down here, this is the venule end. And that got messed up. So this is the venule end. Okay, filtration's going on at the artery end. Okay, so what's happening are things are moving from the capillary out into the interstitial fluid. So it's going that way. Okay, now at the venule end of the capillary, we have reabsorption. So things are moving from the tissue back into the capillary. Okay, so we're really, really good at filtering things out, but we also need to pick things up. So we'll pick them up at this venule end. Okay, so filtration's when it's moving from blood to the fluid, and reabsorption is when it's being picked back up from the fluid into the blood. Okay, now, to explain this, okay, they know way more about this than you'll ever want to know. Okay, so in order to understand this, you have to understand hydrostatic pressure, and you have to understand osmotic pressure. Okay, so hydrostatic pressure, so if you look hydro, right, and like hydraulics or whatever, hydro is pressure from a fluid. Okay, so hydrostatic pressure is basically blood pressure. So it's the pressure of the blood in the vessel. And what it does is it actually pushes the fluid away from the blood vessel. Now, osmotic pressure is pressure due to the amount of solutes that are dissolved in the fluid. And they'll actually draw things into the vessel. Okay, now, let's keep going here. Okay, now, here's the different pressures, and here's the abbreviations for them, because I'm going to show you some formulas. And I don't want you to freak out about the formulas. I just want you to know, in general, how it works. Okay, now, first one is hydrostatic pressure. Okay, so there's two hydrostatic pressures, so two fluid pressures that we're going to look at. The first one's blood, and they abbreviate it hydrostatic pressure, HB, and then the B is for blood. So this is your blood pressure. Okay, so pressure in the capillaries is going to make filtration occur. So it's going to be how we drive fluids out of the capillaries. Okay, so it's going to go this way. Okay, so this would be HPB. Okay, now interstitial fluid hydrostatic pressure, which they abbreviate HPIF. Okay, what it could do, okay, so it's the pressure, so here's the tissue, right? This fluid could exert pressure back on here. Okay, so it could be the opposite of the blood pressure. But normally this pressure is 0, so it doesn't do anything. Okay, so we don't have to worry about it unless something's wrong. Okay, now the next one is colloid osmotic pressure. Okay, so colloid osmotic pressure is the pressure due to these colloids, so the colloids that are dissolved in the fluids. So the first one is blood colloidal osmotic pressure. Okay, so they're going to take colloidal osmotic pressure, so COP, and then they put a little B by it, so it's blood. Okay, now the pressure of the blood, the solvents in the blood, okay, is actually, what's going to happen is it's going to draw fluid in. Okay, so it's kind of like hypertonic. Okay, so if you think of this, the blood has a COP that's higher than the tissue, then the fluid in the tissue is going to want to go towards the blood. I hope that makes sense. It's hard to explain it without looking in your face and seeing if you're understanding it. Okay, so there's an animation too that goes with it. Okay, so basically the hydrostatic pressure of the blood, so your blood pressure, is driving filtration. Okay, the colloid osmotic pressure of the blood is driving reabsorption. Okay, so it's pulling water back in. Okay, the tissue osmotic pressure is due to the solutes in the tissue. The book says it's between 0 and 5, so we're just going to say that it's negligible. You don't have to worry about it. So basically, what's driving movement at the capillaries is blood pressure and the amount of solutes in your blood. All right, now, this might cause you to panic. So basically, here's what I want you to get out of it. Sorry, I had to get a drink of my coffee. Okay. We're going to talk about this thing that's called net filtration pressure. Okay, so NFP. And this is something that physiologists talk about, and they understand like so many things about this. And we're really just getting the basics to try to explain how the capillaries work. Okay, so net filtration pressure, if you had to use a mathematical formula, it's the hydrostatic pressure of the blood minus the hydrostatic pressure of the intracellular fluid minus the colloid osmotic pressure of the blood minus the colloidal osmotic pressure of the fluid. Okay, now this is 0, right? This is pretty close to 0. So essentially, the net filtration pressure is hydrostatic pressure of the blood minus the colloidal pressure of the blood. So the net filtration pressure is going to change. Okay, so let's look at this picture. So here's the arterial right here. Okay, and then here's a venule. Okay, and here's the capillary. Here's the fluid around the tissues. Okay, so at the arterial end, what we're trying to see is that we have a higher blood pressure forcing fluid out than we have colloidal pressure taking fluid in. So if we have 35 for the hydrostatic pressure and 21 for the colloid pressure, the net filtration pressure is a positive. So that means that everything is going to go out, and that's filtration. Okay, now at the venous end, the hydrostatic pressure is going down, okay, because it's slowing down. Blood's slowing down as it goes through the capillary. Okay, so slowing down. The colloid osmotic pressure of the blood is higher. Okay, so it's 21. It's greater than this. So that means that the net filtration pressure is going to cause fluid to go in. Okay, basically, this is what I want you to know. Okay, what's in these boxes? Okay, now, if something's wrong with somebody, some of these numbers could change. Like if someone's hemorrhaging, or they're dehydrated, or they have too many blood cells, it can change these pressures, and it can change filtration.